Sainuddin from Uppsala University, and Ras will talk about non-parametric density estimation in super high dimensions.
Control L.
Thank you. So I don't know, let's see how this goes. I haven't had the time to actually edit it to 20 minutes, but I'll go at Chennai Express South Indian speed in English, right? So this is scalable minimum density estimator for L1 density estimation with universal performance guarantee. So this is the classical problem of the L1 school, right? So there's a lot of co-authors, myself, a couple of my master's students, Axel and Johannes, and then PhD student, not of mine, Thilo, and then Paulina and Lowry, and Warwick Tucker, who is currently in Monash in Australia. Okay, and I must say that it's funded by the Voluntary Autonomous Systems and Software Program, funded by the Knut and Alice Voluntary Foundation in Sweden. So this is the outline. What is this all about, and why do we care? Well, the next point is what do we provide, and the sources of ideas and tools. And finally, what is it good for and how do we do it? I actually want to put how do we do it first and what it's good for before that, but well, anyway. So what is this all about and why do we care? Basically, here's the probability model, standard Kolmogorov probability theories. There are n samples in d dimensions, and the reals are, say, r to the d. And samples are independently generated from an unknown density f, and that belongs to the space of all possible densities in the setting where the densities live, that's L1. So essentially RD contains x1 through xidf, and f is an L1, right? And we want to find the best f in the set of all g's such that the integral of the absolute value of g is finite. So that's the L1 problem. So for a given sample size n, construct an optimally smoothed density estimate. So this can be a multi-dimensional histogram, right? And that's the problem, right? So when you do this optimal smoothing, you cannot cop out and say, oh, f really is an L2. No, that's not allowed, okay? So f lives in L1. When you smooth, you also let f be in L1. That's called universal performance guarantee. So this is the over-smoothing and under-smoothing, so you need to know how much to chop and where to chop, depending on the data. That's the simplest problem. So a lot of this goes back to one of my favorite mathematicians, statistician, Chaffee. I don't know, the legend is he supposedly broke his nose on a fight, so that's a real math stats person for me. So the L1 setting is really driven by the so-called Chaffee identity. So the Chaffee identity says that the supremum of all sets A in the Borel algebra of RD, right, given on the left-hand side, so you simply have two densities F and G, and you look at the L1 distance between them over A, over all A in BRD, so that supremum is exactly equal to 1/2 of the integral over RD of the absolute value of F minus G. So everything basically builds on this, okay? Well, here's the, I don't know, the platinum white wizard who kind of gave me this problem in the World Congress of Probability and Statistics in Singapore, and actually, what was it, 2008? And I think this is the final time I'm going to be with this community, IMS. So we solved the problem, and so what we really want is a computationally efficient estimator with universal performance guarantee. So this means if I'm Google or whatever, I want to do these multi-dimensional histograms over terabytes or petabytes of data if I have the back-end resources, pure distributed computing, no compromise, fixed finite dimension, and sample size n. That's the basic problem, and so it has to be computationally efficient. And we are just using multivariate density estimators with histograms, right? Just think of histograms. And the histogram estimate from the data simply is, it just learns from the empirical data. So we have empirical data, which is mu sub n, and mu sub n simply comes from summing over the indicator functions that you partition. So you have a space, support set, and you have somehow partitioned the data, possibly driven by the data itself. And then, just partition it and count and divide by n. So it's the simplest kernel estimate. Okay, so here is the wizard inside the wizard, right? So this is Yatrikos. I haven't met him in person. We chats in WhatsApp. So he's a Greek-Canadian mathematician who recently returned from China, Beijing. but now he's in Greece, I think, or Vienna, I don't know. So Iatrikos kind of made the next big leap from Sheffe, right? So Iatrikos basically, so Sheffe basically allows us to compare two estimates, F and G, from the data, which is the best, right? And that literally falls out of Sheffe identity. But what if you have K estimates, finitely many, but however large, but choosing the best one from the K, what Iatrikos did is simply generalize the Sheffe sets over all ordered pairs of these K densities. So what's a Sheffe set? Sheffe set is nothing but this A, which is defined by the ordered pair F sub n theta and F sub n omega. So theta and omega are different indices of the histogram. So it's simply the set of all x where F and theta of x is strictly greater than F and omega of x. And of course you also have the other direction. So now if you look at A sub capital theta, which is nothing but all the Sheffe sets, right, in the except the diagonal elements. So that collection of pairwise Sheffe sets is called the Iatrikos class. So one has to do arithmetic and constructions in a distributed system with guarantees on distributed algorithms to actually speed this and compute and find the answer, right? So now, what is the object we're after? The object we're after is this delta sub theta, which is nothing but the supremum of A over the Iatrikos class of the OK things indexed by capital theta, and then you simply take the candidate there, and then you subtract it from the empirical measure. So that's the idea. Right? Then you do the standard ghosting with validation measure and whatever, but that's just bells and whistles. So this is the definition of the minimum density estimate of Iatrikos, which is really nicely written by book by Lugosi, Nobel, Combinatorial Methods and Density Estimation. So the minimum distance estimate psi sub n within the set of estimators in theta. Generally, the Iatrikos class A sub theta is defined to be the estimate minimizing the above distance, the delta guy, right? So that's it. So, and if you have more than one, you choose the smallest index, also generality. So I don't want to go through this for this audience. Of course, this builds on shadow coefficients and VC dimension. So, it's undergrad machine learning course, so combinatorial complexity of the rate of convergence of the empirical measure to the true measure based on the combinatorial geometry of your instrumentation that's measuring the objects in RD, right? But that gets generalized by Lugosi and Nobel, these guys, to partitions. So they generalize VC dimension to partitions, and we basically piggybacking on one of their basic theorems. Okay, so they define a slightly different object than the VC dimension, and it's kind of a jazz on the same idea, but more subtle. Okay. So I have to show this slide. Okay, today in Lisbon, Portugal, in real life, I did a mathematical cuddle with both of them by complete coincidence. I love it because I met him in India World Congress. So anyway, concentration inequality. So yeah, of course, after 10 years, you meet these people and everybody's all old, right? Including myself. Oh, he's the same guy. So anyway, concentration inequality is empirical deviation from true measure. This is the basic theorem. It's really just, these theorems are basically in Luke's book, or they're actually hidden in these papers I mentioned. So what is it? It looks something like this. The probability of the supremum over all partitions in some collection of partitions script A is simply given by the summation of the L1 deviation of the empirical measure from the true measure over all the partitions, right? So this has a concentration bound. That's the main result we use. And then the almost sure convergence of any partitioning scheme. This comes from the Lugosi Nobel paper in 1998, Annals of Stats. Okay, so I'm going to kind of skip over that fast because it's like more than 25 years ago. That's like ancient history in computer science at least. So what is the trick that makes all of this work? Boy, I have like 11 minutes left or something. Okay. So the regular paving is the main object, right? So I want to spend a tiny bit of time on how this actually works. So regular paving actually comes, at least into my world, okay, if you're enumerative combinatorialists and you can read Stanley and they have some names, but these are objects that are called by different communities in different ways. I got into regular pavings from these sort of operations between the French and the English in the English Channel. There's a French Naval Institute and they do robotics and stuff. So they actually use regular pavings for set valued arithmetic. So I come from constructive mathematical traditions in New Zealand before. And so that's where I knew about this. And it took a long time to use this to find the upper class classes. But what is the regular paving? You basically have some compact set, usually say some blocks in some d dimensions, and that's encoded by a tree, and say you partition along the middle, so it can be canonical, like the first widest dimension, and then you can basically encode partitions, these dyadic partitions, using binary trees, right? So the beauty of this is that it's dimension free in some sense, because there is a canonical splitting procedure, and these right and left, or zeros and ones. So you can then use binary numbers to address the labels once you know the bounding box, like really fast. So that's one of the main things we use in the data compression. So mapped regular pavings are an extension of it, so that now once you have a partition, then you can assign values to each box. So you can encode simple functions, histograms, you can put colors, and you can put vector fields. We actually put aircraft trajectories over all of Atlanta, Georgia in a 2016 paper. So it's quite general, mapped regular pavings. And the beauty of mapped regular pavings is that you can actually do arithmetic with them. But before we go there, let's look at the histogram object, which is called statistical regular paving. So it just, data comes in and then falls into these boxes. And you just keep track of counts and divide by the volume of the box and the total number of points, divided in the denominator and how many points in each box. So that's your histogram. So now the other object we need is the collator regular paving. So collator regular paving is very similar. It's just that what do we do when we have two such histograms and we want to collate them, right? So it's basically like a vector arithmetic collation of overlaying these trees on top of each other. So that's basically collator regular paving. Okay, so you can now have, here's SRP, statistical regular paving. Here's a collator, which is a vectorized form of that. And then you can take a statistical regular paving and collate it with the collator, with this box union operator, and then you can just keep track of the heights. But then you see this is 4, this is only 3, and that's the other 3. So the beauty is that it's actually the hidden object making, Thompson's group and geometric group theory. So the beauty of these trees is if you take 2 of them, overlay them, you'll get another tree in the exact same space, where the number of trees at each depth level is defined by the Catalan sequence. So it's a well-studied object. That's mainly thing. Of course, that doesn't work for arbitrary data with arbitrary dimension, and it sounds like crazy, but how does it work? It's because we sparsify them. So we can do sparse regular pavings, which is nothing but the sparse binary tree variant of it, because often there's going to be big holes in the support, and the data is going to be concentrated in random places. So we can go zoom in directly, compress it with the binary label, if you know the bounding box of all of the data. And then you can essentially ignore places where the data doesn't fall, right? So that's the other main idea. So this is actually a sparse representation of a integer valued mapped regular paving with identity element 0. So then we can do classical arithmetic where we have identities 0, just like sparse matrices in MATLAB, right? So you can do arithmetic with sparse binary trees, and that's kind of basically how it looks. And that's what allows us to go to arbitrary dimensions in a distributed way with arbitrary size n. Okay, I want to go too much into it. So how do we justify this algorithm when there is data? So the problem is data cannot flow through the root box that contains all the points. It's a distributed system, so you scatter the data everywhere. So there's a compression stage where you find out the leaf label with the arbitrarily long, possibly arbitrarily long binary encoding. We use like a sequence of long ints for it. And then that means you can go as deep as you want and you get these labels, and then now the point is, okay, that's in the distributed system, so you have to work backwards, right? From the data, which are the leaves of the finest resolution you can consider under your computational budget, and then you have to somehow merge them. So this just uses pure map reduce operations, right? Just map reduce. But then, of course, to mathematically justify it, you have to somehow show that this map reduce arithmetic that's collecting these things is somehow moving through this tree space. And then to formalize that under the Lagosian Nobel conditions, we turn that into a priority queue, randomized priority queue Markov chain. So, and then that has a stopping time, and the asymptotics work out. And the idea is super simple. Basically, from the top-down view, what we do is we choose a box that is populated with the largest number of points at the moment. And then we basically split it. If there are 2 boxes with the same largest number, we randomize it. So that's the randomized priority queue. And the ideas go all the way before Tukey, called the old method called statistically equivalent block from 1948 or so. So what do we provide in the source of ideas and tools? So there's a lot of software for it. So in fact, it's Apache 2 license, so you can use it. People in the industry are using it. Yeah, there's a lot of white papers. This itself hasn't been turned into a white paper yet because we're sort of figuring out how to do this. What is it good for, right? So, yeah, this is kind of, okay, let's look at it's been a mixture of Gaussian densities in 2D cross, right? So you have basically a cross. So we have these lines with different Gaussian densities. Oh, very good. So we constructed a very rich class of simulatable densities. So that we can basically, have like 100 gigabytes and a terabyte of data, and then see how it performs, right? So here is an example of the joint density itself. Actually, this is the histogram estimate. This is the minimum distance estimate. It's indistinguishable to the eye if you do the actual density plot in a MATLAB and then actually do the construction for the MDE, because we're looking at a lot of data points now. And then the general simulation tool, which we kind of made sure I don't have time to go and compare all the methods, I'm not going to do it, but I can produce counterexamples with this family for every method I'm aware of that already crashes R, right? So a lot of the density estimation methods that I know of right now, even the fastest one from Georgia Tech, still require a single random access machine. They need a one-arm architecture with one CPU and one memory. So here, of course, we need to use distributed memory, distributed random access architectures. The classical Apache Spark is what we're using. We're trying to move to Ray.io, if people know what it's about. Ray.io is how ChatGPT is trained. But the point is we need distributed random access memory and we need distributed algorithms, and the asymptotics on the algorithmic end should not only worry about CPU cost, right, which is time, but also the memory cost, how much memory you have in the machine. But it should also worry about the communication complexity of a whole bunch of single von Neumann machines, right? So that's the third dimension. So in fact, Axel's thesis is a lot about the asymptotic analysis of distributed systems implementing this. But going back, we basically have beta-weighted line mixtures of scaled Gaussian locations. So you can have an arbitrary line specified in any dimension, then you can choose a bunch of points there. That will be the location for the Gaussian. And then along that line, we can choose a beta-weighted finite mixture, so like just we normalize beta weights. So then for every line there is a beta parameter, alpha beta parameterized beta that gives you the weights, and then we can also put how much total weight on each line there is. So this is basically the beta weighted line mixtures of scaled Gaussian locations, and that's quite rich enough to produce counterexamples for all the density estimator methods I know, both with L1 and L2 smoothing. Actually, only with L2 smoothing, because L1 smoothed ones don't exist. So dimensionality reduction methods allow projections even from infinite dimensional function spaces. That's the connection with this community. So I don't know, there's a lot of voodoo going on when you do the dimensionality reduction, but it's really useful visualization. And voodoo means the math isn't done, but it's still super useful, okay? So regression analysis is something we really targeted. So for example, we want to do conditional density regression from the density estimate itself, right? I'm not interested in just the expectation. I want to know the entire conditional density. For that, we can do it in arbitrary subsets. So let's say we have C and D are mutually exclusive subsets of the observed variables, and I have condition on D variables, and I want to know the entire distribution of C. So that means we need arithmetic directly on these sparse binary representations of the minimum distance estimate, right? Then we can just slice and dice and do, so arithmetic is directly possible. And yeah, so you can do regression analysis. There's a pet project. I'm still trying to go to the bottom of economics. I still haven't gone past Scottish traditions in 1760s. But yeah, I'm not into economics. I'm going to get into economics. But you can apply it for foreign exchange pairs data. So a lot of this is in our GitHub repost. So marginal densities, from integrating joint densities, you can also do that as a tree arithmetic operation. So you can actually integrate out any subset of the joint density and get marginal densities as a distributed sparse arithmetic representation, right? Yeah, so this is the joint density marginal in X1 and X2. This is the conditional density, so that's what I mean by conditional density regression. And then there are simulators, so because you can do this in any subset of dimensions, right? And then what do you do with this representation? Well, we can simulate from it and actually produce simulations of the conditional density that you want. And yeah, you can normalize it during the probability distribution. You can also do arithmetic directly, but that means addition, subtraction, multiplication, division, as well as all of the standard transcendental functions, sines, cosines, all of that is arithmetically possible directly on the sparse binary tree objects. Okay, so if, for example, you can get 50% highest density regions, 90% highest density regions. This is again an arithmetic. It involves a sort, so we use the fastest sorting algorithm for it because every histogram is basically a bin, right? You just sort it by the height and then boom, get what you want. Well, whatever. It can be used for anomaly detection, right? Because you just basically atomize the sort and then you can just get, I don't know, we did basic law of large numbers checks against the arithmetic. It seems to be good. I think, so there's some examples in higher dimensions. I'm going to skip this. There's some data on training, how much money we blew. I don't know, it's like $800 US for 2 months. I don't know. It's my personal budget, basically, because the grant doesn't allow to charge me AWS. Okay, I think I'll skip. Okay, how do we do it? Yeah, we'll talk about it. This is the main idea. Yeah, thanks for your time.
Now, time for questions. You can ask questions from any of the speakers. Yes?
Yeah, I had a question for you, Rajesh.
Yeah.
So I think I maybe missed it, but where does the bin size come in, and can you do adaptive bin sizing based on local density?
No, the adaptive bin sizing is part of the randomized priority queue Markov chain, right? So basically, I mean, think about it from the top down, that's easier. Forget about distributed computing, so we do all this thing with machine a long time. So yeah, you basically have a bunch of leaves right now, because the data is there, and then you simply choose the leaf with the most points right now, right? And if you have 2 or more, you choose that at random. So that already does, that's the statistically equivalent blocks principle. And that already gives you asymptotic consistency using Lugosian and Nobel results, right? But things get more weird and beautiful when you go backwards, right? Because you have to take the data point and immediately put it in one of these finest resolutions up to your computational budget, right? It means encode it, sample data from partitions. So each leaf is assigned a weight, sort data according to, so there's a left-right ordering on the tree. So there's a data compression step first. And then you have to start merging them. So that's where the distributed computing stuff. So it's like the backward process is kind of, it's mathematically trivial. There's nothing fancy going on theorem-wise. But on the distributed computing end, it took us years, basically.
Thank you.
Go ahead.
I have actually 2 questions for you.
Okay.
Very nice work, by the way. One is related with the choice of the uniform kernel. If you're doing a histogram, I guess you don't care because you have petabytes of data.
Yeah.
Would it be possible, as a curiosity, to do it for a non-uniform kernel?
Oh man, you want like Gaussian and stuff? Okay.
Yeah.
Look, no, you can. So it's about various things, right? So we're actually developing an entire distributed sparse tree arithmetic, right? So if you can work with simple functions, and you read like some of the oldest classical books on analysis from 1880s, right? These I don't know, people from Netherlands, I forgot his name. It's called set-valued functions. So if you can work with simple functions, right? Just constants over even dyadic partitions, right? That's a lot of reanalysis comes out of the wash, right? I mean, so we were basically targeting just that as one of the simplest arithmetics one could do. When you have Gaussian kernels and stuff, what happens is things spill over partitions, right? Yeah. So then you have to do all these clever tricks they do in Georgia Tech. So they have very good kernel density estimators there, right? But they use very clever triangle inequalities to know when when the Gaussian far away is like very little contribution. But okay, so yeah, in some sense, yeah, it's unfortunately inspired heavily by the underwater submarine robotics in the French Navy. It's good enough for them. So you have compact sets, and you know that your object is somewhere in there, and the arithmetic is easy. But if it spills outside each cell, then, I mean, I don't know how because these are discrete objects, right? So, do you see what I mean? So when I overlay 2 trees, right, just with a couple of leaves, they go 1 or 2 levels deeper, right? Then it's easy to do. But then if your objects, if the maps are actually saying, there is a kernel that sits in this leaf, but it spreads itself everywhere, that's like too much. So it's kind of an arithmetic convenience, okay? But operationally, in the big data space, I hope it doesn't matter. I don't know. I'm not trying to make money with this. So.
Another good question I made, I didn't get very well how well this scales on the dimension. I understand it scales very well on the sample size of the dimension.
Yeah, so that's... I can say honestly that it's not a trivial problem to fully answer. So we had a lot of, so we work with uniform data first and then Gaussian line mixtures, right? Strange things happen in this representation. What do I mean by strange things? So counterintuitive things happen. So because you have a computational budget, right? Because you can't have infinite bit strings to represent the leaves. So which means if you have some say 10 dimensions, so we play with 10 dimensions a lot, then for the same fixed computational budget, you're going to, if you think about it as leaf depth limits, so you have to go deeper and deeper in higher dimensions possibly, depending on the entire data configuration, right? But then you might need like very, very long binary strings for it. So think about that. So that enters into the picture. But beyond that, also, you have classical asymptotic issues, right? Rates of convergence are affected by points and dimensions as well. So I don't have a perfect answer to it, but at least for the uniform, interesting things happen because in uniform density, which is the most entropic, dimension doesn't matter. Okay, so this is so we have a lot of results that we will have in this paper that tell you how, but for line mixtures of Gaussian in 10D, it really depends on the structure of all the lines and the weights. All of these things, the global structure enters the encoding, it enters everywhere. So I don't know. It's like too much. Somebody else can work on it. Yeah.
So again, related to this stuff.
Sorry, I'm hijacking all the questions.
It's fine. It's fine. Just as fresh as in mine. Is it correct to understand that the sparsity is only introduced by the computational budget?
No. Well, okay. So this is that's a really beautiful question. So I'm thinking extreme, right? So if I have 100 dimensions and I have arbitrary Gaussian line mixtures, like some lines don't even penetrate the other dimensions and stuff. Let's say it's really complicated. Then what this will imply is that I have to enclose the entire box. So this is the downside. So the first thing I need to do is take all the points, which are floats, right? Vector floats, like lots of rows. I need to find the minimum and maximum in each dimension. That's a straightforward map-reduce operation. That gives me the one big mother box or whatever. And then I use that and then some other encoding tricks to then take every vector of data point and quickly turn it into a binary string, right? So to find the leaf. Okay, so finding the box is easy because it's a map-reduce, min-max. But then when I do this, I can also do some clever things. But then it may be the case that if I say I want every data point to be in its own leaf, this is the ultimate paranoid operation, right? You could do. Then in that extreme setting, you will have to formally say this is my computational budget, because I can use long integers and a vector of long integers to keep increasing my bit arrays, but that will blow your budget as well, right? So what we sort of forced ourselves is, okay, we can't actually compress the data beyond your computational budget itself, but then all of the 10D stuff and all of the examples we've done, that's fine. You can do with just academics like pocket money in AWS, right? So,
but then you have sparsity if you have an unlimited budget. That's also my question. The other way, would you still end up with sparsity if you allow whatever budget?
No. Without sparsity, we can't do anything. So it's absolutely sparsity. But I'm saying even on top of sparsity, I can construct with these Gaussian line mixtures samples such that your tree has to be so deep, right? Think in 1D, right? Think about it. If I go like 0.0, I can just blow up my one real number, I can blow my computer budget, right? So I have two really, really long real numbers, and then I say I want them to be, in their own leaves, and they're arbitrarily close to each other. Okay, I'm being a constructive math guy now, right? So they can actually fall between the cracks of two adjacent floating point numbers. That's extreme. So I'm thinking from that extreme point of view. But for most of the stuff, operational stuff, like say you're working in aerospace or something, no issues because they don't work more than a single, right? So they don't even work with doubles, right? So that's fine. So if you're just working with doubles, of course, then with dimension, what happens is tuples of doubles make things you have to go deep, even if you use sparse trees.
Okay, thanks guys. Let's continue over the coffee break. So, thanks.